So, what came before the Big Bang? Religion, such as Hinduism, it says that time has no beginning, but is infinite and cyclic, rather than a universe coming from a Big Bang. In the Encyclopedia of Hinduism, it shows several Big Bangs following it in a pattern. It also says that the Big Bang Theory reminds humanity that everything came from the Brahman, which means a subtler than the atom, greater than the greatest. Now, we don't know what came before the Big Bang, but there are theories that the universe was hibernating until something set it in motion. This idea is saying before the Big Bang, there was a small, flat, high-pressure space that was stable until it found an even more stable state. Like a house of cards might sit perfectly solid forever until a breeze came through. That breeze came through and it stopped being stable and inflated the universe. So basically, this is the breeze. It came through here and it made it bigger. What was the universe like during the first moments of the Big Bang? Now, we don't know exactly what happened before the Big Bang, but we do know what happened in a tiny fraction of a second. It was extremely hot and dense. It was filled with neutrons, protons, anti-electrons, and more. 300,000 years after the Big Bang, there was an era of recombination in which protons and electrons combined to form neutral hydrogen. Now it's 13.7 billion years. It is what we have today. There are 4 fundamental forces: gravitation, electromagnetism, strong interaction, and weak interaction. Moving on to the emergence of the fundamental forces of physics. Gravitation holds together the universe at large, plus the atmosphere, water, and us to the planet of Earth. The electromagnetism governs atomic level phenomenon, binding electrons to atoms and atoms to one another to form molecules and compounds. The weak interaction radioactivates and decays of certain nuclei. Strong interaction attracts force between protons and neutrons, keeping the nucleus together. Electromagnetism, weak interaction, and strong interaction were made by particles. Gravity was caused by the curvature of space-time. The expansion of the universe during the Big Bang. Think of it as a balloon. The balloon analogy is a 2-dimensional model, and the center of the balloon and the space around it is not part of the 2-dimensional universe. Photons move and redshift colonies spread apart and stay the same size. Now, momentum was the idea that the universe received all the energy. How a space expanded, the universe cooled and mattered form. This was discovered by Edwin Hubble.
In the beginning, the universe started as light energy in the form of photons. Photons are bosons, meaning that they decay into other particles. These particles are known today as matter and antimatter. The idea that matter came from energy makes sense when scientific laws are taken into account. Einstein's famous equation, E equals mc squared, shows that mass and energy are related. Energy is determined by mass times the speed of light squared, and mass is determined by energy divided by the speed of light squared. Thermodynamics also support this theory, with the existence of a law of conservation of energy and a law of conservation of matter. Both laws tell us that neither energy nor matter can be created or destroyed, but that doesn't mean that they can't transfer between each other. They both point to one key idea, that energy is related to matter and matter is related to energy. But that still doesn't show us the whole picture because there's 2 different types of matter and antimatter. What is antimatter? Well, its name is very fitting because it is essentially the opposite of matter. An antimatter particle is the same exact thing as a matter particle, but with an opposite charge. If a matter particle has a positive charge, then the antimatter particle has a negative charge. If a matter particle has a negative charge, then the antimatter particle has a positive charge. When the 2 combine, they cancel out and explode. Naturally, there is more matter than antimatter, so matter won and now makes up the majority of the universe when comparing only matter and antimatter. Even today, though, there are still antimatter particles in our universe, and scientists have even been able to create some of these particles in controlled labs or particle accelerators. But even with matter, the universe didn't look like it does today. Electrons are flying around freely without orbiting around nuclei, so the universe looked like a chaotic, soupy plasma. As the universe cooled down, the electrons lost energy and began to settle down and orbit around hydrogen and helium nuclei, which created the atoms we know today. The photons from the beginning were set free after this, which will be important later in the formation of the known universe. At that point, the soup was gone, but there was still more room to grow. To understand the next point of development, we need to understand space-time first. The universe is like a fabric, and that fabric is space-time. When matter sits on the fabric and makes a crater in it, the denser the matter, the denser the crater. When there is a crater in space-time, other particles with less density pull towards the denser matter like a ball rolling down a hill. The new atoms created had differences in temperatures, which means they had differences in density. The colder, denser atoms gravitated towards the less dense atoms due to space-time and began to form clumps. These clumps got hotter and hotter until eventually they became hot enough for fusion to occur, and stars began to form. Now this is where the photon particles come into play. These photons are everywhere in the universe and today are known as CMB, cosmic microwave background radiation. Scientists eventually began to map out their existence to determine multiple things. First, the photons show us the entirety of our observable universe. Secondly, small inconsistencies in the CMB help us understand the formation of our universe. It proves the existence of space-time, which was responsible for the formation of stars and eventually galaxies. Finally, the CMB shows a record that dates back 380,000 years after the Big Bang. This sounds astonishing, but we can go back even further. Gravitational waves, ripples in space-time as a result of cosmic events, show us even more, going back all the way to 10 to the negative 36 power to 10 to the negative 32 power seconds after the Big Bang. Also, have you ever wondered what the static on the TV is? The visual static is the CMB photons, and the audio static is the gravitational waves. Pretty mind-blowing stuff. But even though our universe is vast in size and in historical time, new scientific discoveries have shown us that our universe is bigger than we first comprehended. Edwin Hubble studied a star named M31 and its differences in light. With the invention of the Hubble telescope, he discovered that M31 is not a star but a galaxy 2 million light years away. To provide some perspective, our own galaxy is less than 100 light years big. This new galaxy is known as the Andromeda Galaxy, our closest neighbor, and it proves that there are billions of galaxies and billions of stars so far away that we'll never reach them. And, if that wasn't scary enough, Hubble also discovered that our universe is expanding. As a galaxy wavelength hits our Earth, the wavelength lengthens and reddens as it travels away and shortens and turns blue as it comes closer. From observing distant galaxies, Hubble realized that they are traveling further and further away and our universe is expanding. But why does our universe expand? Well, this is where uncharted territory begins. Scientists believe that there is dark matter and dark energy in the universe, energy and matter that is undetectable. The dark matter and dark energy exist in the empty space, and like regular matter and energy, they are related to each other. There is evidence of dark matter from light being altered by areas with high concentrations of dark matter. But how do dark matter and dark energy cause the universe to expand? Well, dark matter is essentially the opposite of matter and antimatter. Instead of attracting matter and antimatter with alterations in space-time, it's repulsive. Since there is more dark matter and dark energy than matter and energy in the universe expands. It is also theorized that dark energy is getting stronger, which is causing the universe to expand faster. Because matter is expanding, there is more empty space, so dark energy, the energy of empty space, gets stronger. But as amazing and mysterious our universe is, eventually it will have to come to an end. It is officially unknown how our universe will die, but there are a few theories. The Big Rip theory predicts that the universe will expand faster and faster until it pulls everything apart, even atoms. The Big Freeze theory predicts that the amount of entropy will eventually reach a maximum, and energy will be evenly distributed as the universe expands. This means that there will no longer be usable energy, and everything will have to come to an end. Heat death theory predicts that the universe will become so big that gases won't be able to meet and make stars, so the universe will cool down and die. The Big Crunch theory predicts that the expansion of the universe will stop, and the universe will collapse in on itself and form singularity similar to the one from the Big Bang. And finally, the Big Slurp theory predicts that a vacuum will exist in the universe at some point and expand at light speed, destroying everything in its path. But don't worry, even though the death of the universe is scary, we'll all be dead long before then. Thanks for watching.